Hey guys, it's me again, Nathan. Today, I'm back with another cool and exciting video. So what should we do? Just watch it. So today we're going to talk about quantum tunneling. Quantum tunneling is one of the phenomena which occurs in the quantum world. So they're different, including quantum entanglement, which you've probably heard about. But the reason I chose quantum tunneling is because it has many practical uses, and also it is an amazing topic, an amazing subject to talk about. And so let's start with this meaning. Quantum tunneling is, as you can understand from its name, the tunneling or the passage of microscopic particles through seemingly impossible boundaries or potential barriers. So those potential barriers have more height than the energies or the kinetic energies of the particles. So when we normally analyze that problem, if something or some object does not have enough kinetic energy to penetrate through some potential barrier, it's just going to bounce off, or it's going to get stuck, right? But in the quantum world, things are a little different, because particles have a probability of appearing on the other side of a potential barrier, even though they don't have enough energy to penetrate through that barrier. So a simple demonstration will be, if there's a hill, like if there's a road which has a slope going up and coming down, then if one person tries to push a rock or just a ball with his hands and give it some kinetic energy, that is not enough to go up the hill all the way. What's going to happen? Simple. It's going to return back. But in the quantum world, that ball or that particle can go all the way up and down. So that's why it is called quantum tunneling, because particles can penetrate through barriers with a minimal possibility or probability, but some of them can escape. So that's why it's different from our world of understanding. So the history of quantum tunneling is started in the studies related to radioactivity. So as you know, Marie Curie and Pierre Curie were nominated for a Nobel Prize because of their works in radioactivity. So after the studies of radioactivity and also alpha decay by George Gamow and other two scientists named Robert and also Edward Condon, the Schrodinger's equation allows a possibility for particles to penetrate, or half-life particles to penetrate through barriers. So those barriers are in the range of 1 nanometer to 3 nanometer in thickness, and there have been many experiments done on them. So the first person to notice this quantum tunneling effect is known as Frederick Hunt, and other two physicists independently named, the first one was Micheli and also Leonid Mendelsohn. So the two scientists and Frederick Hunt noticed the possibility of quantum tunneling while driving equations for potential well barrier. And it's all related to the Schrodinger's equation, so which I may cover in my next video. So there had been different experiments and different theories on how quantum tunneling works and its uses. So the first experiment was done in a lab facility, or in the Swiss, or in the Institute of Swiss Technology in Zurich by Urella Keller. So Urella Keller is a physicist who works in the Switzerland's Institute of Technology, and that was the first ever accurate, or more accurate, or the most accurate measurement ever done on quantum tunneling. And the main problem that scientists had was that the tunneling time, or when a particle tunnels through a barrier, that barrier makes it faster than it would normally travel. So, for example, if there's a particle, and if it goes from point A to point B, and it takes some time, that means we can calculate speed, right? When quantum tunneling occurs, what you would expect is, if there is a barrier, there is going to be a decrease in speed, right? That's what I thought, but that's not what happens, because when a particle is guarded by a potential barrier, its speed actually increases, and the speed of the particles in the potential barrier are actually found to be faster than light. So superluminal speed became possible. So scientists argued that this quantum tunneling effect is instantaneous, and nothing can travel faster than light, so it can ruin, or it can disturb, the general relativity theory of Albert Einstein, which says that nothing can travel faster than light, right? So, but other physicists argued that if superluminal information transfer is not done, it does not disrupt the quantum tunneling's faster than speed of light phenomena, because if information is not transferred in that speed, then it's not a problem. So in Urella Keller's study, she used a measurement called attoseconds, and it was found to be 50 attoseconds. 50 attoseconds means 50 multiplied by 10 to the power of minus 18 seconds. So that's how much time it took in the potential barrier for the particle to penetrate. So that's a lot less than the speed of light, which is 300,000 kilometers per second. So superluminal speed was found to be possible. So the other thing or argument made about that specific experiment was that it did not encounter the initial position of the particle, because we took the time it took from the potential barrier to the final destination, but we didn't know where it started from. So a more precise and specific measurement was needed, and for that we've got Ephraim Steenberg. So Ephraim Steenberg is a physicist in the University of Colorado, and his experiment was the best ever. So what Ephraim Steenberg did was, he did two experiments, and the first one was with two of his colleagues. The first one is Ramos and other colleagues in the Toronto University. So they managed to tunnel 1% of the original 100% optical source or photons through a barrier. So what they noticed was that that there was a barrier time which was about 1.8 attoseconds in the barrier. So many physicists argued again that this experiment was the same as the Keller's experiment, so they did another one. But in this one, they used a clock system called Larmor's clock, and it was designed by magnetic fields and laser fields. So when rubidium atoms generated or they were tunneled through that specific laser beam as a potential barrier. So there was a laser beam used which was about 1.3 microns thick, which was used as a potential barrier for the rubidium atoms to tunnel through. So when they tunneled through it, the Larmor's clock can identify how much of time they took in the barrier while they were in the barrier. So it was found out that the particles or the rubidium atoms took about 0.61 milliseconds, so which does not make it instantaneous. And many physicists believed that using the Larmor clock was the best solution for getting the accurate representation of the potential barrier time it takes for a quantum tunneling particle. Amazingly, quantum tunneling has a range of different uses in the universe, and the first one is cancer cells or DNA mutations, cancer cells, and also aging. These all are related to quantum tunneling. And how, you may ask, how is quantum tunneling related to the sun's light or insolation? Well, I'm here to tell you that. The sun's light is generated by a series of nuclear fissions like other stars. So our star works that way too. So for a light to be generated, the same proton particles have to fuse together, and there's a repulsion force between them. So if there were no quantum tunneling at work, the sun would not light at all, because if the repulsion force wouldn't have been cancelled by the tunneling effects of protons, it would stay that way, and the sun couldn't have shined. So it's the first importance of quantum tunneling, and the other one is scanning tunneling microscope. And scanning tunneling microscope is discovered by Gerd Binning. His name is so weird, I keep forgetting it. So Gerd Binning, and also another physicist. So it also uses the use of quantum tunneling effect to determine or to observe very little microscopic objects, which would not be possible to observe with normal electron microscopes. So these are the two main uses of quantum tunneling, and it is also used in the quantum computing system. Quantum computers are the future of technology because they can store a lot of data than we might even think about, because they use effects of quantum tunneling and other quantum mechanical effects to work, and it's a lot complicated than only quantum tunneling. But quantum tunneling has also a use in the effect of quantum computing. So these are the three main uses of quantum tunneling at work. It is important to differentiate the differences between superluminal speed and superluminal speed information transmission, because superluminal speed of particles means dust particles which are transmitted through through barriers or through the vacuum or through some medium faster than the speed of light. And information transmission faster than the speed of light is not possible according to the relativity theory of Albert Einstein. So superluminal speed of particles is possible, but superluminal information transmission is not. So quantum tunneling, what it does is superluminal speed of particles, so it does not violate the rule or the law of relativity or causality. A lot of things in the quantum world are weird, like so much. Like you cannot expect particles to pass through barriers like we talked about. So a physicist named Gracefield said that quantum tunneling is weirder than quantum entanglement because of all these systems joined in a spooky way. So Albert Einstein called the quantum entanglement spooky action at a distance. So we gotta find a name for this one too, because this one is more complicated and interesting than quantum tunneling. So it was all about quantum tunneling. I hope you learned something new today. So it was me, Nathan, from TechNatty. So don't forget to subscribe to my channel and like my videos to be a family of this growing channel. I'm not going anywhere. I'm coming 2 days later with another astronomy or any science related video. So comment down below what you think about the video and what I should do better. And I love you all. Thank you.